The Sharpe ratio is one of the most computed and reported statistics in finance. Yet for 6 decades, finding a closed-form expression for its distribution under realistic assumptions remained an open problem. This video explains how this long-standing problem was solved. Introduced by William Sharpe in 1966, the Sharpe ratio divides an investment's expected excess return by its volatility, the reward earned per unit of risk. It anchors modern portfolio theory, guiding how investors report actual and backtested performance, identify new investment factors, rank, hire and fire portfolio managers, optimize portfolios, etc. But a Sharpe ratio computed from data is only an estimate, and to trust it, we must know its sampling distribution. In 2002, Andrew Lo's landmark paper, The Statistics of Sharpe Ratios, gave the first rigorous treatment. For independent returns, he derived a clean closed form. The variance is 1 plus half the Sharpe ratio squared over the sample size. For dependent returns, he turned to the generalized method of moments and Newey West estimation, powerful but not a closed-form expression. Then Michael Wolff, in a 2003 comment in the Financial Analyst's Journal, spotted a subtle but important oversight. Lo's tidy formula quietly assumed normality. The term 2 sigma to the fourth holds only for Gaussian returns. With the fat tails real markets show, confidence intervals become too narrow, giving a false sense of security. Thanks to Wolff's careful reading, a general analytical expression clearly remained an open problem. Elmer Mertens, also in 2003, answered part of the challenge. He corrected Lo's formula to account for skewness and kurtosis, restoring honest confidence intervals for non-Gaussian returns. But Mertens still assumed returns were independent over time, a real limitation, since investment returns are known to exhibit strong serial correlation. Wolff's challenge remained unanswered. In 2025, Marcos Lopez de Prado and Emilio Porcu published a unified foundation in their paper on the asymptotic distribution of the Sharpe ratio under weak dependence and non-Gaussian returns. They established primitive conditions, finite moments and alpha mixing, under which the Sharpe ratio is asymptotically normal, with a single, interpretable variance decomposition valid far beyond the classical IID Gaussian case. Building on this, in 2025, Marcos Lopez de Prado, Alexander Lipton, and Vincent Zunichind delivered the long-sought closed form. Allowing returns to be jointly non-normal and serially correlated, their variance combines the first-order autocorrelation rho, the skewness, and the kurtosis of returns. An analytical solution matters. It makes inference transparent and auditable and keeps portfolio optimization tractable with no opaque resampling. How accurate is it? In 10,000 Monte Carlo simulations with only 60 monthly observations, the generalized closed form tracks the true sampling variance across every scenario, while the old IID normal formula understates it, often by a factor of 4 or more. Correct inference, even in small samples. The frontier moved again. Marcos Lopez de Prado, Emilio Porcu, Vincent Zunichind, and Robert F. Engel extended the theory to GARCH returns with volatility clustering and heavy tails. Their model-free result identifies the bottleneck. When the true mean is non-zero, if both the sample mean and the plug-in Sharpe ratio are square root n regular, then the empirical quadratic scale must be square root n regular too. If heavy tails break that scale regularity, the Gaussian Sharpe ratio approximation itself can fail. In the finite fourth moment GARCH regime, they derive a closed-form variance that separates a skewness channel from a volatility clustering channel. Their formula holds up too. Across Monte Carlo simulated GARCH paths with sample length from 50 to 1,000, the generalized expression converges quickly to the true variance, confirming that the closed form delivers accurate inference under realistic returns with volatility clustering. A 60-year-long quest, distilled, Sharpe defined the point estimate, Lo opened the question of its sampling distribution. Wolff and Mertens exposed the role of non-normality, and the 2025 and 2026 papers delivered a unified theory with closed-form variance under joint serial correlation, non-normality, and volatility clustering. The distribution of the Sharpe ratio is at last understood. This body of work turns the most used financial ratio into a rigorous, testable statistic. To find solutions to many other open problems in finance, visit quantresearch.org.